In today's video, we're going to define what we mean by a vector space. We will also look at several vector spaces and look at a few identities for vector spaces. Now, from this point on, this course is going to become extremely rigorous and abstract, meaning that the videos henceforth will contain a lot of proofs. Now, a useful procedure in mathematics, as well as other disciplines, involves the classification schemes. The idea is we form classes of objects based on properties that they have in common. This allows us to develop notions that apply to every member of the class based on the properties they have in common. This helps us work with more abstract and comprehensive ideas. Such a classification in linear algebra is the notion of a vector space or a linear space. So a vector space consists of a set of objects and two operations on these objects that satisfy a certain set of rules, which we will now look at. The set V, together with operations of addition and scalar multiplication, altogether denoted as V plus dot, is called a vector space if the following conditions are satisfied, and there are 10 of them. If U and V are in V, then U plus V is also in V. That is, V is closed under the operation of addition. So if you have two vectors in your vector space, their sum must also be in the vector space. This is what it means to be closed. U plus V equals V plus U for all U and V in V. All right. So addition is commutative. U plus V plus W, this is supposed to be a plus here, equals U plus V plus W. So addition is associative. There exists an element Z in V such that U plus Z equals Z plus U equals U for all U in V. This element is called the additive identity of V and will be denoted as 0, the 0 vector. For every U in V, there exists an element D in V such that U plus D equals D plus U equals Z. This element is called the additive inverse of U and will be denoted as negative U. Those 5 were for the operation of addition. The next 5 are for the operation of scalar multiplication. And it starts the same way. If C is a real number and U is in V, then C times U is also in V. In other words, V is also closed under scalar multiplication. C times U plus V equals CU plus CV. So scalar multiplication will distribute across addition. C plus D times U equals CU plus DU. So scalar multiplication will also distribute across regular addition. CD times U is equal to C times DU. In other words, the order in which you do your scalar multiplication does not matter. And 1 times U is equal to U. 1 is thus called the multiplicative identity. In other words, no matter what vector space you're working with, 1 must be the multiplicative identity. To completely describe a vector space, 1 must specify 3 items. We must specify the set V that we're working with. We must define the operation plus, and this does not need to be standard addition. And we must also specify the operation dot. And again, this does not need to be the standard scalar multiplication. We now look at several defined vector spaces. One we've been working with our entire lives, and that is the set of real numbers under standard multiplication, standard addition, and multiplication. Another set is a set that we just started working with, and that is the set of all m by n matrices, denoted as big M sub mn, with addition defined as standard matrix addition, and multiplication defined as standard matrix scalar multiplication. Another set is the set of all n vectors. They are n by 1 matrices represented as r to the n, right? Again, remember that r represents set of real numbers. And the set of 1 by n matrices, denoted r sub n, under standard matrix addition and matrix scalar multiplication. Notice that this is just a special case of the set of matrices. The set of all continuous functions defined on a closed interval AB, denoted as CAB, with addition defined as the standard function addition, and scalar multiplication defined as standard function scalar multiplication. Right, so here we have a chart of some of the important vector spaces. Right, so we have the set of all real numbers, the set of all ordered pairs, the set of all ordered triples, and the set of all ordered n tuples, right? So that's R, R2, R3, Rn. We have the set of all continuous functions, as well as the set of all continuous functions on some closed interval. The set of polynomials, the set of polynomials degree less than or equal to n, together with the zero polynomial. Right, so again, these three are actually special cases of C minus infinity to infinity. Then we have the set of all m by n matrices, and the set of all square matrices. Once again, this m and n is a special case of the set of m by n matrices. Let's now look at a vector space that does not have standard addition and scalar multiplication. So we're going to look at the set of all positive real numbers with addition defined as x plus y equals x times y, and scalar multiplication defined as c times x equals x to the c for all x and y in V and all real numbers C. And the question is, does this form a vector space? Right, so remember, in order to form a vector space, it has to satisfy these 10 properties. So first, let's check if it is closed under addition. Right, so for all x and y in V, we know that x, y are real numbers. which of course means that x times y is a real number because we know that the set of real numbers is closed under multiplication. Well, that means that x times y would be in V, right? Because V is the set of positive real numbers, I should say. Right, so plus, plus. Right? So xy is obviously a real number, and since they're both positive, it's going to be positive. X times y was defined as x plus y in V, right? Second one we had to prove is that addition is commutative. So for all x, y, and V, x plus y is equal to x times y. But we know that multiplication of real numbers is commutative. So we can write that as y times x, which is y plus x. And the reasoning being is that x and y are positive real numbers. Third, we had to prove associativity. So for all x, y, z in V, we're looking at x plus y plus z, and we want to regroup this. Well, by definition, this is x, the grouping of x times y times z, which is equal to x times the grouping of y times z, which by definition is x plus the grouping of y plus z. Right? We can do this because we know that multiplication of real numbers is associative. Right? So this is because x, y, and z are all positive real numbers. 4, we have to prove the existence of an additive identity. So for all x in V, look at x plus 1. This would equal x times 1, which is x itself, right? Again, because we're dealing with positive real numbers. This means that 1, which we know is in V, right? Because 1 is a positive real number, is the additive identity. We also have to prove additive inverse. Well, let's call it 1 over x. That would be x times 1 over x, which is 1, our additive identity. And we know that 1 over x is also a positive real number. So 1 over x is also in V. And this is the additive inverse. That proves the 5 for addition. We now need to look at the 5 for scalar multiplication. So first, prove that it is closed under scalar multiplication. So we know that x is a positive real number. So x to the c would also be a positive real number. So this means that c, I don't know why I put parentheses there, c times x is in V, so it's closed under scalar multiplication. Right? So we look at all xy in V. We want to show that scalar multiplication distributes across addition. So c times x plus y is equal to c times x times y by definition of addition, right? So this would be x times y to the c. Right, that is x to the c, y to the c under standard rules of exponents. But that is cx times cy, which by definition is cx plus cy. And this is because, right, again, x and y are positive real numbers. Number 8, right, we take an element in V and two real numbers, CD. We want to show that scalar multiplication also distributes against regular addition. So take C plus D times X. Right, this is X to the C plus D, which is X to the C times X to the D using properties of exponents. Right, well, that is Cx times dx, which is Cx plus dx. Right, and again, because x is a positive real number, we can use these known properties. Number 9, right, for all x in V and all real numbers CD, we look at CDX, and we want to show that this is equal to C times dx. Well, by definition, that's x to the CD, right, which we can write this way, x to the C all raised to the D. But by properties of exponents, we know that this order doesn't matter. We can write this instead. Right, so this would be C times x to the D, which is C times dx. And again, this all works because x is a positive real number. And finally, we have to show that 1 is the multiplicative identity. So for all x in V, 1x is equal to x to the 1, which equals x. And again, because x is a positive real number. All 10 properties hold, so we say, therefore, this set V together with vector addition and scalar multiplication as defined is indeed a vector space. We will now close out by looking at 3 particular properties. First, the additive identity of a vector space is unique. So to prove that something is unique, we say, suppose that there are 2 of them. So suppose there exists 2 elements y and z in V such that u plus y is equal to y plus u, which equals u, and u plus z is equal to z plus u, which is also equal to u for every single element u in our vector space V. Then, let's take a look at z. Well, since z is in V, this is equal to z plus y, right? Because we're saying that y is the additive identity. But we're saying z is also an additive identity, so that is just equal to y. Hence, z is equal to y, which means there is only one identity, right? We assume there are 2 and show that they're actually the same. And so the identity must be unique. If V is a vector space, then the following 3 hold. 0 times u is the additive identity for every u in V. C times the additive identity is still the additive identity. And C times u equals the additive identity means that either C is 0 or u is the additive identity. All right, so to prove the first statement, for all u and v, we're allowed to write 1 times u, or u is equal to 1 times u. But this is 1 plus 0 times u. Right? And then because it's a vector space, we can write 1u plus 0u. Right? But 1u is just u. Right? But this must equal simply u. Right? So if we subtract u from both sides, we get that the 0 identity, right? We're adding the u inverse, is equal to 0 times u. Right? And this is because the additive identity is unique. Second statement. Let u be an element of V. Now, from the first statement, we have that 0u is equal to 0. So, therefore, for all real numbers C, we have C times the additive identity is equal to C times 0u, which of course we can write as C times 0u, which equals 0u, which is again the additive identity as desired. So if you take C times the additive identity, you just get the additive identity back. Finally, the third property. If C is equal to 0, then C0 is the additive identity for all u in V. I'm sorry, that should be C times u, right? That is obvious, right? That is from property 1. Now, if Cu is equal to 0, but C is not 0, right? Then we can write u is equal to 1u. Let's write that down here. Right, but we can write that as 1 over C times u, which we can write this way, 1 over C times Cu. But Cu is 0, right? So we have 1 over C, 0, which is just the additive identity. Which is what we wanted. And so all three statements have now been proven. And finally, we're going to show that the additive inverse is unique. Right? So each element of a vector space has a unique additive inverse. So for all elements u in our vector space, let D be an element in V such that u plus D is the additive identity. Adding the additive identity minus u, write it this way, minus 1u to both sides yields u plus D plus negative 1u is equal to the additive identity plus negative 1u, right? this would then lead to d plus u plus minus 1u is equal to just minus 1u, right? Because 0 is the additive identity. Grouping doesn't matter, so I can write this, d plus u plus minus 1u. That is equal to minus 1u. Now, if we use axioms 10, 8, and Theorem 2 Statement 1, the left-hand side will yield d. So we get that d is equal to -1 times u. So we're showing that we assume that d is another additive inverse. This is actually equal to the original additive inverse -u. So this shows the additive inverse is unique, which is what we set out to prove. And that concludes our introduction into vector space. Right? So we defined what a vector space is. We looked at several important vector spaces. Looked at an example where we had a vector space where addition and multiplication were defined in an unusual way, and then looked at several properties. In the next video of this series, we will look at what is known as a subspace. As always, thank you for watching this video. Hope you learned something, and I will see you all in the next video.